So we know that we're not going to get 100% because there's a lot of factors that go into play. But we want to figure out how efficient a reaction is. An example, when you can look at a bunch of different stats on, let's say, basketball players, that's what we have here, and you have a bunch of different stats, and you can try to look at different things to see how efficient they are. You can see points per game or something like that, and that's how you can find efficiency for athletics and basketball players in this case. But when we're looking at this, we have two different reactions. We need to be able to do the same thing. Which reaction is going to be more efficient? Now, both of these reactions can produce sulfuric acid, but the second one is more efficient. So the second one is more likely to produce sulfuric acid more efficiently, and we're able to get more of our product, okay, closer to that 100%. So that is where percent yield comes into play. Percent yield gives us that quantitative value that we can actually say, hey, this reaction is more efficient because it has a greater percent yield. So when we're calculating percent yield, this is how we do it. We start with a balanced equation because, yes, this is stoichiometry. Always starts with a balanced chemical equation. We identify the limiting reactant and calculate the maximum amount of product that can be produced, which that's the theoretical yield. We measure the mass of the product that's actually produced. Okay, I would say that this is done in the lab. So you're actually recovering it, it's actually sitting in front of you, you actually put it on a balance. Okay, that's what you get in the lab. And then you just use this formula here. Percent yield equals 100 times our actual, which that's what we get from the lab, and then divided by our theoretical, which I would put next to theoretical, math. You have to calculate the theoretical yield. Okay, the actual yield comes from the lab, the theoretical yield comes from math. So let's go ahead and jump into an example. It says, example B1, 1,500 grams of zinc is available to react with 200 grams of copper 2 sulfate. This is the resulting yield of copper is measured to be, so this is what we actually measure. What is the percent yield of the reaction? So remember, if we have our actual, because it says this resulting yield of copper is measured to be, so that's what we actually have. That's our actual yield. The only thing we need is our theoretical yield. So we need to calculate what our theoretical yield is, and we do that by starting with our limiting reactant. So on this, we have to find our limiting reactant. We always start with a nice balanced chemical equation, because that's what all stoichiometry starts with. We've used this reaction a lot before. We used it in the lab. It's one that we should be used to. So copper 2 sulfate. We have our copper, which it's 2 sulfate, SO4, which is 2 as well. So we'll get our equation of copper 2 sulfate is CuSO4 plus we're adding zinc metal. So it's just Zn. And they switch places. Now, all the oxidation numbers are the same, so everything's just going to be a 1. So we have copper plus our zinc sulfate. Okay, so when all the oxidation numbers are the same for every single thing in the equation, you're not going to have to balance it. It's all 1s because they're already all balanced. So going into this, since we have our balanced equation, now we can actually start with the problem. So we'll have 1,500 grams of zinc, and we have 200 grams of our copper 2 sulfate. Now, just looking at this, since all the ratios are 1 to 1, in this case, since there's so much of zinc and so little of copper 2 sulfate, more than likely copper 2 sulfate is going to be our limiting reactant. But let's figure that out. So zinc is 65 grams per 1 mole, and in one reaction we have 1 mole of zinc. So we go ahead and multiply and divide, and we get 23.08 in a reaction. and then 200 grams of copper 2 sulfate, which copper 2 sulfate has a mass of 100, right around 160 grams per 1 mole. And again, it's 1 mole in one reaction, which we multiply that out, and that's going to give us a much smaller number, which is 1.25 in a reaction. Okay, so that's going to be our limiting reactant. So we start there. We really don't need zinc anymore, so we'll get rid of it. We need the space. So if this is our limiting reactant, let's find our theoretical yield. So we start with our 1.25 in a reaction, and we're trying to find, since it's the resulting yield of copper, so we're looking for copper. So in one reaction, we have 1 mole of copper, and then all we have to do is just get it to grams, because we see that our actual yield is in grams. So 1 mole equals our molar mass of copper is 63.5 grams. Multiply that out, and we should get a theoretical yield of 79.4 grams in a reaction. All right, not in a reaction, but 79.4 grams of copper, which is our theoretical yield. Now, this is a place where you can kind of put a note. Your theoretical yield should always be more than your actual yield. If it's not, then you did something really wrong. So all we have to do to finish out the problem, our percent yield equals 100 times our actual, which is 70, all divided by our theoretical is 79.4. So divide first and then multiply by 100, and we should get right around 88.2% yield of copper. All right, another example. It says the combustion of propane is determined to produce 93% of the expected carbon dioxide. What mass of carbon dioxide is produced when 200 grams is combusted in 100 kilograms of oxygen? When we're looking at this, it told us what the percent yield is. Okay, remember that we can always calculate the theoretical yield. So the problem, what it's asking for is it's asking for, well, what's the actual yield? So if I know that this reaction it's 93%, that's what I'm going to get. That's normally what happens. Then how much is going to actually come out of this? Now, one thing I'd pay attention to, we see that this is in kilograms, and it's a huge number. So we have not just 100 kilograms, that's, we think of it as 100,000 grams of oxygen. So if I have 100,000 grams of something and then I have something with only 200 grams, what do you think is going to be the limiting reactant? Well, obviously it's going to be our propane. Okay, so since we can do that, we've already determined, yeah, definitely going to have excess oxygen, which we should, because there's oxygen in the air. We should never run out of that. We have 200 grams of propane. All we need to do is calculate the theoretical yield, and then we'll multiply it by our 93%, and that will give us our the actual yield that we should get in the lab. So work it out. We have 200 grams of propane, C8.3.2. Okay, and one thing that we always have to have, no matter what, is we got to have our balance equation. So we can't forget to do that. So we have our C3H8 plus our O2 produces CO2, because it's a combustion, plus H2O. So to balance this out, we go ahead. We have 3 carbons. We need 3, so we put 1 right there. We have our 8 hydrogens, so I'll put a 4 right there. Look at our oxygens. We have that 3 distributes, so we have 6 plus that 4 distributes, so 6 plus 4 is 10. That works out because we can make that 10 on the other side. So there's our balanced chemical equation. So when we're working this out, all we're doing is trying to find the expected carbon dioxide. So you can think of it this way. We're going from our 200 grams of this to our carbon dioxide. And we can skip the step where we find out how much is in the reaction, because we already know that the 200 grams of propane is the limiting reactant. So from here, we can just go ahead and say, well, it's just a gram to gram conversion now. So we need the molar mass of our propane, which we find that out to be right around 44 grams is 1 mole. And we look at what's the mole ratio between these two guys. It's 1 to 3. So 1 mole of our C3H8 equals 3 moles of our CO2. Okay, not done because we need to have it in grams because we want to find out what's the mass of carbon dioxide produced. So we go from moles back to grams, which carbon dioxide has a molar mass of right around 44 grams for CO2. So multiply everything out and we should get something right around 200 times 3 times 44 all divided by our 44, and we should get something right around 600. So we get 600 grams, and that's how much CO2 is produced. So when we're looking at this, all we have to do here is we have 600 grams that can be produced, 93% of it. So all we have to do is, since we know what the percent yield is, we just multiply our 200 times. And remember, whenever we multiply by a percent, what do we always have to do? Move the decimal. So we multiply by 0.93. And we should get 600 times 0.93. And we should get something right around 558 grams should be our actual yield that we get.